Okay, hello everyone and welcome back to this amazing series of video related with electromechanical conversion systems. As you must be aware, when we are designing or specifying any electrical machine, one of the most important aspects is the efficiency. And efficiency is connected to the concept of active power losses. And inside a electrical machine, one of the very important aspects related to electrical power losses is all the magnetic phenomena inside the magnetic material. So I have been recording this series of video for all the viewers and my personal students, and this lovely video today is dedicated to a practical example estimating and calculating the active power losses in magnetic material. This is the question Q3. This is the last question of this tutorial, and I hope you can enjoy this video today. Without further delay, let's start reading this amazing statement. And as you can see over here, the alternating iron loss density Pi in a laminated, sorry about this typo, laminated iron sample was 2.2 watts per kilogram, and Bm equal 1.2 Tesla and frequency 50 Hertz. In other words, we know the alternating iron loss density at this very specific operating condition, maximum magnetic flux density 1.2 Tesla and 50 Hertz. And we know the constants of this material. We know Kh, Ke, and Kx. And also we know the very important statement index 1.7. Now, the interesting question over here is calculating the alternating iron loss density in watts per kilograms. As you can see, now we want here in watts per kilograms, but a frequency of 100 Hertz, and keep unchanged the maximum flux density Bm equal to 1.2 Teslas. So this is a very practical and realistic example, and as you can see, the answer is over there, and the number that we need to get is 6.98 watts per kilogram. Many of my students, they attempt this problem, and also they come back to me over email with very interesting question, but let me clarify straight away the solution, okay? Here, I want to show you the step-by-step solution. So the starting point, you must remember this amazing equation over here. We have been using this equation in classes and for many weeks. And this equation says that the alternating iron loss density, in this case in units of watts per cubic meter, has three different terms. So what is important to us is that the iron loss density that is provided here in this example is in a different unit or coming from this equation. As you can see, the units that we are receiving is 2.2 watts per kilograms, and this equation with those terms over here is working in watts per cubic meter. So a simple solution will be, okay, let's convert these 2.2 watts per kilograms into watts per cubic meter. All my students, they will be tempted to do that. What you need to do is multiply 2.2 watts per kilograms by the material density. But the important problem here is we don't know the material density. So this approach over here that many of my students, they want to try at the very beginning, it was not possible. So what we need to do is be clever with the data that we have and how we can use that data. Because if you look over here, we know KH, KE, and KX. And also we know BN and F. So this equation can be directly applied to obtain the iron loss density. So why not? We apply for the first term. KH is 115, 50 Hertz, 1.2 Tesla. We obtain here the component for the hysteresis. Then we know KE, and that is 16. We know 50 Hertz and 1.2 Tesla. And we obtain the second component that is related to the eddy current losses. So then what we need to do is basically calculate the excess losses, and in this case we are using here KX, that is 12, 50 Hertz, 1.2 Tesla, and we obtain PX. So finally, what we need to know is combining these three components, we obtain here PI. But this PI is in unit of watt per cubic meter. PI, the alternating iron loss density, will be 19,176.3722 watts per cubic meter. So now we will do something extremely exciting. We will do something extremely exciting because I will come back to the original idea of using the density. At the very beginning, I didn't use the density because the density was not provided. But now I know this value because this is provided in the statement. This is 2.2 watts per kilograms. And we know here, we know on the other side, we know that is 19,176.37 watt per cubic meter. So the left-hand side of the equation, we know this. On the right-hand side of the equation, we know this. So the unknown value is the amazing density. So what we will do is, let's extract the material density, and the material density will be Pi in watt per cubic meters divided by Pi in watt per kilograms. So these watts will cancel with these watts, and at the end, using the double C, the unit will be kilogram per cubic meter. So when we substitute, remember this is 19,176 watt per cubic meter divided by 2.2 kilograms per cubic meter. So finally, the density is 8,716.5328. Some of my students, they will say, oh, this sample density is huge. The reality is that this density, 8,700 kilograms per cubic meter, is a bit high. But if you look into the tables from the physical properties of material, you realize that there are several metals, for instance nickel, that they start in 9,000 kilograms per cubic meter, and then when you have alloy with them, you can reach almost 9,000 kilograms per cubic meter. So this density is realistic, and now we will use this value, this density, to calculate the final answer in our question 3 over here. So let me keep going now. Here in this example, we has been asked about the alternating iron loss density in watts per kilogram. But for this very exciting condition of 100 hertz. So again, what we need to do is use this very important equation that is the combination of three individual terms, one term related with pH, one term PE, and one pH. So using the numerical values and applying the numerical substitution, you can see over here that we obtain a total, an alternating iron loss density of 54,492.96 watt per cubic meter when we apply a magnetic field with 100 hertz. So this alternating iron loss density in watt per cubic meter now will be converted in watt per kilograms, because we were asked to give the final result, to provide the final result in watts per kilograms. So now what we need to do is use the sample density, and now to obtain watt per kilograms, what we need to do is divide this number that we obtained before, watt per cubic meter, divide by the density. So as you can see, the cubic meter will cancel each other, and when we put the number together, the losses, and in this case watt per kilograms, is 6.9863 watt per kilograms. What is interesting to reflect over here is that this value is at a frequency f2 equal to 100 hertz with a Bm of 1.2 Tesla. But what is interesting is that we were given another point, and in this case it was 2.2 watts per kilograms, but for a frequency of 50 hertz, considering the same maximum magnetic flux density, 1.2 Tesla. So the main conclusion over here is moving the frequency from 50 to 100 hertz, I mean almost doubling the frequency, that is almost more than 3 times increase on the alternating iron loss density, because we are moving from 2.2 watts per kilograms to 6.98 watts per kilograms. So this is the end of this very entertaining, very educative, very knowledgeable video today. I hope you are enjoying this amazing learning experience. I hope that you find this video very useful, and I wish you all the best in this learning experience. And this is the end from this video today. Thank you very much for watching, and I will see you at the next one. Bye now.